I've been with Planetary for 3.5 years, and it was founded about 4.5 years ago at the end of 2019. We'll get into what Planetary is all about in a minute, but for myself, I did the first, sort of 20 years of my career in the Canadian Forces, and then moved into government with Natural Resources Canada. So I pivoted into sort of decarbonization and energy transition work with the Office of Energy Research and Development at Natural Resources Canada. In the military, I was a mechanical engineer. That's my training. And through my work with the government, after leaving the forces, I was working with a lot of very innovative companies from coast to coast to coast, doing all sorts of different projects to really, reduce our carbon footprint and GHG. And I came across Planetary that was just being started up at that time. And I know the CEO and co-founder from my school days, and we got to talking, and I eventually decided to join. It's been quite the adventure the last 3.5 years. What I have today is sort of just touches on the surface, but we can dive into any topic that interests people. And I've had a couple of different roles. So when I first joined the company, because of my government background, I was doing a lot of what we call external relations. So working with funders and government agencies to, prove out the pathway for demonstrating our technology. And then about 1.5 years ago, I switched into a more operational role, which kind of drew on my military roots and took our technology from the lab into the field. And we've just completed, well, not just, we completed our first big pilot in Halifax Harbour at the end of December. And we're just wrapping up the reporting on that now. So it's good timing. And then really exciting for us to announce, because it's now public as of yesterday noon, is we're one of the top 20 finalists out of 1,300 teams for the $100 million carbon removal XPrize. So if you've heard of XPrize, that's something that that we're in the final running for, and so that's a lot of our thank you. That's a big excitement for our team right now. Anyway, so I did put some slides together, and I don't know if Dustin, if you can watch hands. I do have everyone on my screen here, but if someone has a question, please feel free to interrupt. And I don't know what sort of level of knowledge everyone has when it comes to carbon removal. So I do have a couple of slides that go into that, but we can skip through that if it's something that's already been covered in this group.
No, I think we're game for that sort of science background stuff. That'd be great for us.
Okay, perfect. So Planetary Technologies is, as you might have seen on our website or in that first slide, our mission is to restore the climate, heal the ocean. And so the founders launched this company with the ambition of having a big impact on climate change. So in other words, doing something about all of the carbon, the excess carbon in the atmosphere from all of our industrial activities over the last 200 years. And Dr. Greg Rao, who is the brainchild who's been working on this problem for a while, had developed an approach to generating alkalinity that can be essentially added to seawater that would induce a flux of carbon into that, induce a flux of carbon into that seawater by converting excess carbon in the seawater into bicarbonate and carbonate. So I have a slide on that in a minute, but this slide explains why would we want to do that. So we know, we need to drastically reduce emissions to zero as quickly as possible. But in addition to that, we have to do something about the excess carbon that's already in the atmosphere, which is going to have an impact on warming and climate change for some time to come. And we also know that certain industries are going to be very difficult and expensive to decarbonize. So even when we've done as much decarbonizing as we can of our energy system and whatnot, there's certain things like process emissions that right now will likely, or aviation, that are going to be very difficult to reduce. And so we need to be able to remove that carbon if we're going to hit our net zero targets. And that's effectively what this is showing here. So IPCC has said, by 2050, up to 10 gigatons of engineered carbon removals. So this is not capturing carbon from point sources. This is actually figuring out ways to take carbon from the atmosphere and then permanently store it in some sort of reservoir, whether that's underground, in the ocean, in some sort of durable product. So that's, yep.
Yeah, thanks, Jason. Did you say, was that 10 gigatons per annum per year?
That's the current projections. Yeah,
and that's what's going to be needed. Okay.
Yeah.
Okay, yeah, that's not an insignificant number. So.
Not at all. No, and so to put that into, I mean, you can see it here on this chart. Like if emissions are peaking around 50 gigatons a year of carbon dioxide equivalent, and so that's 20%, right, of our current emissions are what we expect, and half of that is like hard to decarbonize, and then half of that is essentially excess emissions that we're trying to draw down. So, and then if you look at it, up until 2100, cumulatively, you're looking at around 1,000 gigatons. So it's a lot. It's a big. So it's huge, right? And so there's a couple of challenges with that. One is around energy. So it's not a very thermodynamically favored activity. Be taking even though there's excess carbon dioxide in this atmosphere, it's still 423 parts per million or whatever it is today. So getting that out of the atmosphere is an energy intensive process. Most pathways, right? And then once you've separated that carbon dioxide or figured out how to draw it out of the atmosphere, it's like, where are you going to put it? And so that's the other big challenge. So Planetary's solution, essentially, and it's not, it's, here we go. There's a couple of ways that we address those challenges. Again, focusing on carbon removal. So when it comes to storage, the biggest carbon sink in communication with the atmosphere is the ocean. Obviously, the ocean is the majority of our planet. It's 80% or 88% of all carbon dioxide that's in communication with the atmosphere resides within the ocean. It resides within seawater in the form of carbonates and bicarbonates. And the ocean has actually been doing an outsized role in terms of mitigating the effects that we're already feeling of climate change. I mean, anyone in the marine sector is already aware of this. I don't have to tell you, but 90% of the heat and roughly 3 gigatons a year of carbon dioxide are absorbed within ocean chemistry, and it's leading to devastating effects, especially the heat in terms of coral reefs and other loss of biodiversity. But we're also seeing ocean acidification, and if you're on the West Coast, that's a big concern. That's already impacting things like shellfish and whatnot. So the process that we basically are commercializing is taking alkaline feedstocks, adding that to existing outfalls, existing pipes, whether it's wastewater treatment plants or power plants where we've been demonstrating the technology to date, monitoring that for say all sorts of reasons, right? And then we can get into that, and then essentially modeling the reaction that occurs when you've added that alkaline material to seawater, disperses very quickly, and then induces this reaction. So dissolves, you have bicarbonate and carbonate forms. The pressure differential now between CO2 in the seawater, surface seawater, and CO2 in the atmosphere is different, and an influx of CO2 goes into that seawater, and you're effectively drawing it out. So the ocean becomes the CO2 is effectively locked within the seawater chemistry for millennia, and at the same time you're reducing ocean acidification. You're helping to neutralize that CO2. So I'll pause there and just see if there's any questions about this. I don't think this is most people are somewhat familiar with this concept, but I'm happy to dive into it if there's any questions.
Does that bicarbonate precipitate out onto the seafloor? Is that where it goes?
Not if we do it correctly. Some of it's a good question, because some of it, obviously, seawater isn't just seawater. There's a lot of living things in there. So some of it will be used, which actually goes against our, we have to account for that when we think about where does all the carbon go, because some of it will actually be used by living organisms to form their shells and whatnot. But if we add it in a way that doesn't lead to precipitation events, then no, it just stays, within the chemical formula of seawater, essentially. It shouldn't precipitate onto the seafloor. That's one of the things that we have to monitor.
I gotcha. Thanks.
Not really a question, Jason, but definitely affirming, the impact of acidity in the ocean is more and more been showing up in aquaculture industry, shellfish industry. Like you get massive die-offs of in these industries where they've been working for decades, and it's like, an event happens, you get some, it's not always just like things going up over time, but you're getting more and more of these problems. And so that alone, of like that environmental impact from all of the dissolved CO2 increasing acidity is a huge issue. And so I'm really excited to see more about what you're doing.
Yeah, so the interesting thing here, we can get into this a little bit. So this approach, the CO2 storage problem, which is a big one, is, essentially we're accelerating natural weathering of alkaline rocks is what we're doing. And, this excess CO2 over time would eventually end up in the form of bicarbonate and carbonate in the ocean. That's where it's going to go. If we stopped emitting tomorrow and there was no human activity, eventually the oceans would balance out. The oceans and atmosphere would balance out. So this process essentially speeds up that natural process. But in order to do that, the alkalinity that we're sourcing can't be produced in a way that's emitting more CO2 than you would remove, clearly, because you're not really helping the overall problem if that's the case. So that's a big part of what we do, and I'll talk about that. And it's true, like, the alkalinity that we're currently sourcing is already used in things like wastewater treatment plants for pH balancing to reduce the acidity of effluent being discharged into the ocean, or in some cases in aquaculture. It's being used already to try and deal with acidification, as you mentioned, Ryan. So this is kind of going a bit more into how our particular carbon removal solution helps to address some of the issues with different carbon removal pathways. So I don't know how familiar people are with carbon removal, but there's dozens of different pathways. A lot of people are familiar with direct air capture, which is just, big fans essentially sucking in lots of air, absorbents that capture the CO2 and then they heat up, release the CO2 and then pump it underground. Carbon engineering, which is, got their R&D facility based out on the West Coast. They're developing that kind of technology. There's a lot of electrochemical approaches as well, where, for instance, maybe you're taking in seawater and stripping out CO2, separating that CO2, putting it underground. The issue with those approaches, as I alluded to at the beginning, is they're very energy intensive. So it's competitive. You're essentially competing for green electrons with other industries that are trying to decarbonize, whether it's the power sector in general or transportation or whatnot. So this process that we've developed, we're sourcing alkaline feedstocks that are already available, testing them to make sure that they're suitable for addition to the ocean environment. And then we're using existing infrastructure, existing pipes. So we're not adding, obviously there is energy and pumps and whatnot, but it's a fraction of the energy for some of these other more energy intensive processes. So it's a way that we can prioritize green electrons for decarbonization type activities while also ramping up carbon removals, which we know are going to be required. The other thing too, I'll just to nail this point, is that we're not talking about capturing from a point source. This is in fact carbon removal, so it's completely additional. And I think I mentioned the storage already, which is a big issue for different technologies. If a lot of the expense related to sequestering carbon is having a place underground, if you're doing it terrestrially, to do that, to monitor that, and then also having the pipelines to move that CO2 around. With a marine approach, or working with the ocean, you essentially are creating that ocean surface becomes like the biggest air contactor, and you can affect both the removal and the storage in one process. So how do we do it? This kind of gives you at a high level, sort of how we're working today. We call this the ocean carbon platform. This is kind of overly simplified, but so we are sourcing alkalinity that currently is like a byproduct of other processes. So for instance, right now we're qualifying a material that is a byproduct of magnesia production or MgO production. It's like a kiln dust. And we know, we've looked around, and even in North America and Europe, there's about 400 million tons of this type of product that is currently not being used. It's sitting there. On its own, it will actually naturally carbonate. And that's often what happens. The surface layer, you'll see that these piles are carbonated. But by being able to move them to a site like an ocean site, processing them a little bit, and then discharging them into an effluent stream, you can accelerate that natural carbonation process, and then at the same time turn that into bicarbonate in the ocean. When you're looking at the capacity of pipes, so we're working with right now 3 wastewater treatment operators in the UK, US, and in Canada, and we have 1 power plant where we did our pilot, which I'll show you in a second. But based on those outflows, we can generally say that the capacity to do this with existing pipes and existing pumping capacity is around 7 billion tons. So it's massive. And as we already talked about, it's helping to neutralize ocean acidification. So our technology is really the combination of sourcing and qualifying the alkalinity, the monitoring system, the automation and the pumping system that sits on site, and then the modeling that happens in the monitoring within the ocean. Those 3 aspects together, and then basically calculating through software what the carbon credit potential is and the timeline to retire those credits. So that's what we call the ocean carbon platform. Any questions so far? Yeah, Dustin?
Yeah, so that's amazing. I was just wondering about that 7 billion ton number. Is that the CO2 number, or is that the byproduct number?
It's the CO2 removal potential. So
Okay.
that's a very, I stole this from an investor deck. So it's a very high level estimate, just to show you, what the potential here, that this can scale to a gigaton process. There's a lot built into that, right? Like you need to parse that out. That's just saying that the pumping capacity, assuming things like current permit conditions for most of these pipes in terms of pH and TSS and stuff is respected, based on the modeling regions. So looking at things like, how, I'm not the oceanographer here, but in order for this process to work, the alkalinity has to remain within the surface waters for a period of time to allow that reaction to occur. So it's looking at things like ocean currents to make sure that you could actually affect that carbon removal.
Wow, this is amazing. Thanks, Jason.
Yeah.
What kind of power plants are you looking at there?
Yeah, it's a good question. If I read into it a little bit, so right now we're working with a thermal power plant in Nova Scotia. And so the obvious question from that is, well, don't we need to, ultimately move away from those power plants as quick as possible? And yes, yes, we do. So, we think in the short term, there's an opportunity to sort of develop and grow this technology using the infrastructure that's being used today and will be for some time, as this energy transition takes place. But ultimately, that plant could become fully just a carbon removal plant, right? So a lot of these areas, and we're working with thermal power plants. We've had conversations with nuclear power plants, which obviously have huge amounts of cooling water. But for the stage that we're at and, the size of our company, the regulatory sort of red tape of working with a power plant was something that we didn't want to do at this stage. But I think it is something that we, would make sense in the future. So hopefully I wasn't reading too much into your question there, but it's not lost on us that we're working with, fossil fuel power plants at the moment in order to demonstrate a carbon removal technology. I think it's a means to end at this stage.
Well, I think also it's not an either or situation. It's like we need all the technologies and everything that we can do. There's already massive amounts of too much dissolved carbon, CO2 in the ocean. Even if we did, like you said earlier on, magically have all renewable power everywhere, we still have this problem of all that imbalance of embodied carbon everywhere, right? So.
For sure. I mean, and I can tell you, I spent quite a bit of time on our site in Dartmouth last fall. And it's funny because, we're working very long hours. It was pretty manual labor, which I'm not used to these days. So it was really, you'll see in the video here coming up. But, it's impressive. These power plants are pretty impressive, but you realize how big the challenge we have is ahead of us, because that's just one power plant. I mean, there's 5 of those and similar scale in Nova Scotia. 1 million tons of CO2 per year that they need to figure out what to do with. And in the time that we operated, for 62 days that we operated our plant last year, we removed less than 100 tons. So the scale is just, you got to start somewhere, but you just, when you're out there in the field, looking at the smokestacks, looking at what you're doing and realizing how hard it is, it's a big challenge for sure. Okay, so unfortunately I was not able to, I don't think I was able to get the sound working, but what I'm going to play this video, it's about 1.5 minutes. What you're going to see is, so this is obviously a bird's eye view of our system, which we call SAM, Site Automation and Monitoring System. We have, a telehandler here, which you can see just, I don't know, can you see my mouse? Do you see my mouse? No? Okay.
I don't see it.
So these white bags here, one that the telehandler has, these are sacks of alkalinity. It's magnesium hydroxide, brucite that we worked with an American supplier to source. We're mixing it in this blue tank here, and you'll see this in a second, to create a slurry. So seawater and magnesium hydroxide slurry. This is where all of our controls and pumps are. It goes into this ISO tank, 25,000 liter ISO tank. And then you can see there's a pipe going into this outfall here. Now, if you look at the outfall itself, it's all pink. This film actually happened to be taken when Dalhousie University, who we partnered with on the monitoring, was doing dye tracer studies. It's not normally a pink discharge, so I'll just say that up front. But anyway, I'll play this video and hopefully you can see it big enough on your screen. Oh, I think I have to do it here. And I apologize, no sound. So as you can see, it was pretty manual, having to untie each of those bags. We ended up doing 278 of those over the 62 days. And this is Robert. He designed this whole system. So that's what the slurry looked like. And then we had these sensor boxes that were essentially continuously monitoring pH, TSS. Oh, here you go. In addition to that, we were also monitoring at a mooring about 50 meters away. So, yeah, and that's our chief scientist, Dr. Burt. You can kind of get an idea of the plume here. Again, this was, the white on the surface water there, that's actually always there, whether we're discharging or not, because there's about a 14-foot drop from the outfall, from the cooling water into this little cove. Hold on a second. So that gives you sort of an idea of what this looked like. This video, like I said, it was taken when we were doing dye tracer, and it was a very nice day, but there were some not so nice days. A lot of, as you can imagine, Halifax, I remember our first week starting, it was in September, and we had a hurricane warning and had to batten down the hatches. That's when we actually had to get all of these concrete barriers and stuff in. And then since what wasn't shown in there, but we were doing our monitoring included things like sediment sampling. Dalhousie was out there with a boat doing water quality sampling, and we've just completed our report looking at all of that, all of the results, and we're submitting those to an independent crediting agency to take a look at the modeling and all of the measurements that we took throughout the 62 days. Is there any questions on that? Okay.
I've
So-
got a question actually.
Yeah, sure. Go ahead, Ryan.
Can you tell us more about the magnesium hydroxide material itself? Like just from a, general kind of characteristics. I'm not a chemist or chemical engineer. Like, is it volatile in any way or, by itself?
No.
Or what?
So we actually, we went for magnesium hydroxide because it is considered, it's very slow reacting. It's like a slow release alkalinity. And actually what we learned during the trial is that, so we're not going to spike pH, but then the opposite problem can happen where it doesn't react quick enough and you can have some settling on the sediments. So we monitor that very closely. We did see evidence that there was some, not visible, like you can't actually see it. And so we're continuing to monitor. But that was one of the aims of the trial, was to figure that out. For this year, we're actually moving towards, it's a mix of magnesium and calcium hydroxide. So to try and have a more reactive alkalinity that will dissolve quicker and achieve the same effect. And I see a question that is, yep. Sorry, there's a question here, I think, in the chat. Yeah, minimum maximum temperature for your system to operate without heating or cooling. It's a good question, actually. I don't actually know the answer. I could probably follow up with that. It's not set up to for overwintering right now, so we shut it down over the winter, and we did monitor. Like part of our modeling was recognizing that the seawater that we were using, that we were adding this slurry to, is heated from the power plant. So it actually helped our monitoring because you can very clearly delineate the plume. So we can correlate temperature when you're in or out of the plume, and then look at the chemical signatures that we're trying to measure on in and out of the plume too, to see if try and isolate any sort of signal from our alkalinity. The reality is that we because the magnesium hydroxide is slower reacting, and because we were adding it at such a low concentration, it was very difficult for us to detect any variation in the outfall. We can measure it we can see the difference directly where we added it into the outfall pipe. It's actually a bit of a waterfall in this case, because we had a sensor box upstream and downstream. But in the outfall itself, it's not detectable. So hence the dye tracer, so that we can validate the models. And then at this stage, we're pretty reliant on those models to tell us what's happening, because it's, like I said, very difficult to detect with sensors. Great. Okay, I'll keep going here. Oh, just try and play the video again. Okay. So, I mentioned a big part of our process is testing the alkalinity. I'd say it's probably the biggest piece. So last year we had sourced 2 different forms of magnesium hydroxide. One actually came from Baymag. So if you're out in the West Coast in the Rockies, there's Exshaw, Alberta, where they produce magnesium oxide. And there's a company in the States that imports magnesium oxide from Canada hydrates it and then dehydrates it into a magnesium hydroxide, and it's a very high grade product. So we use that for a week. There's no carbon removal benefit when using a product like that, because it's, to generate magnesium oxide, you have to start with magnesium carbonate or magnesite, and so you're burning off, an extra. They burn off the carbon dioxide from that rock, then you're transporting it. So it was the purpose of that week trial was to see if using a very pure product that's already used for commercial activities, if we can measure the signal. So we did all of that. Then we used a brucite, which I mentioned, which was same supplier, but this is actually just mined naturally. So it's naturally occurring magnesium hydroxide. It's not calcined in any way. It's not cooked in any way. So it's got a very low footprint. The only energy required is having it ground. But because the only naturally occurring magnesium hydroxide or brucite occurs in primarily China and Russia, the transportation emissions basically make it very marginal in terms of removal. So even though we were able to claim some carbon credits with that, it's not a viable source for scaling this up or even making it, economically viable. So we've been at the same time working on a number of what we call byproduct alkalinity sources and qualifying them. And so these are things that are coming off of like lime kiln dust or kiln dust off of magnesia production. And this year it's before the regulator right now, but we're looking at using a magnesium kiln dust from a production in Spain. So obviously we're getting transportation down quite a bit. And because it's a product that comes off of another primary product, the emissions that are attributed to it are much smaller than the primary product. So again, reducing the carbon footprint. And it's also a more reactive material, so less risk of it settling on the sea floor or not actually doing the reaction that we want to see in the surface waters. So that's what we have planned for this year, and we're hoping to get up and running again. Well, the schedule has us up and running again mid to late July, and that's what we put forward to XPrize to be one of the top 20 teams moving forward this year. So, and I think optimizing this in the future, we need to be looking at sources that are even closer. So we have a big push to look at what are mineral sources in the province that we could potentially develop in the future when the scale justifies that sort of capital expenditure. Again, it's tricky because you want obviously everything we do comes with a carbon footprint, so everything has to be optimized to make sure that you're not it sounds really obvious, but it's very tricky, the logistics of doing this type of operation. Okay, I think I'm coming to the end here, and then I mentioned the carbon calculator. So here you see sort of what the modeling looks like. This is actually, I believe, the model of 1 week of addition in late August, and so you can see where the alkalinity is ending up over that 1 week period. And from that, we can calculate sort of what the carbon removal potential is within the harbor. So it's those three elements coming together: the dosing system you saw in the video with all the sensors measuring or putting into the outfall, the qualification of that alkalinity, and really focusing on the logistics and minimizing the footprint of getting that alkalinity to the site. And then in the end, modeling using the inputs from the measurements to validate and refine the model to ultimately generate the carbon credit.
So where does the magic happen? Is that in your tank or in the ocean?
So if we do it right, it shouldn't happen in the tank. Now, one of the things that so in the ocean is the short answer to your question. But one of the things that we learned with the sizing of our ISO tank, so I showed you that big 25,000 liter ISO tank, is that the residence time of our slurry in that tank, some of it was carbonating in the tank. So you're getting less of a benefit. You want that to all carbonate, react fully in the seawater to form a bicarbonate instead of just a calcium or a magnesium carbonate. So 2 for 1. So this year we're actually optimizing that, and we're we did a batch system last year where we would mix 3 or 4 batches in that blue tank that you saw, and then it would sit in the ISO tank, and then we would, over a period of time, dose into the outfall within the pH and TSS limits that were set out for us. This year, we're looking to run a continuous system. So we'll have a much smaller tank, reduced residence time for that slurry. And so we'll be, sort of bringing in seawater and dosing dry alkalinity into that tank continuously without storing it in a big tank where there's potential for precarbonation.
So Jason, the precarbonation is that just sucking carbon out of the air, or where is that carbonation happening? Because obviously, I think the point is like you want to take the carbon out of the body of water, not like, oh, we took some out of the air. Then you're putting all the stuff in the water, it's doing less than you hoped, right?
That's the idea. Yeah, exactly. So we want to optimize. We want all of that. I mean, there is some carbon benefit, even if you pre-carbonate it on land. It's just not the most efficient way to do it, right? So the most efficient way to do it is to discharge the alkalinity directly and not hold on to it and incur all of the energy of mixing and trying to hit that right optimum pH so that on the spectrum you're getting mostly bicarbonate and less carbonate, right? I hope that makes sense. Like, again, I'm not the chemist here, so I always my domain is making sure that everything operates safely on the site and with the equipment. Our marine chemist could give you a much better explanation than I am, but that's the idea.
Maybe one question here. I guess the idea is to always be operating so that the outflow is safe for the ecosystem, essentially. Is that the goal?
Yes, absolutely. So safety is, I didn't really touch on that as much as I maybe should have, but that's the number one priority. That's why we're doing all these very small scale tests and then slowly looking to ramp up as we've got the data to back up that it's safe. So part of the alkalinity qualification process, we're doing all of the ecological testing in closed environments with, local species using prescribed Environment Canada LC50 tests, to make sure that it's not a deleterious substance, to understand exactly what the potential thresholds would be. And we're operating at orders of magnitude lower than any potential impact level, or I think it's called the LOEC, limit of no effect. The no effect concentration is essentially we're operating well below that. So obviously then there's a question of, scalability, right? Like how much can you do this at any given time and over what period of time? And so that's what this longer duration trial that we're going to be doing this year. We're looking at 6 months of operating versus 2 months. And the idea there is to see if, over a longer period of time, in addition to optimizing our dosing system, which I just described, it's like, do we start to observe things that, could indicate that over a longer period of time that there's impacts here that we need to account for and be aware of. So that's a big part of what we're doing right now.
Cool.
Yeah.
Any other questions, guys?
Yeah. What's the pH that's coming out of this system when you're discharging it?
Yeah. So I'm thinking back. I think we're the pH coming in versus the pH going out. It's you almost can't even see it. But I want to say like it was, if the input was like 8.1, the output was like 8.12 or something like that. Like it's very, very small changes, which is actually part of the challenge, which is why we're looking at going to more of a blended alkalinity this year that has a little bit more faster reacting or faster dissolving components so that we can actually see that change. Our permit, we were permitted to operate between 6.5 and 9, and we came nowhere close to that. Like the seasonal, like the tidal, like the variation we saw from like tidal or storms or natural events was far in exceedance of any variation we saw from, the variation we saw at the mooring sensor, which is 50 meters away from where we were dosing, was much greater than what we saw right at the pipe upstream and downstream of where we were dosing. So we know from that our input was having little effect at the scales that we were operating.
Cool. One more question I touched on at the start with the precipitate. I'm still struggling to understand what the CO2 turns into and where it goes.
Yeah, so the way I've heard our our chief ocean scientist describe this, which kind of stuck in my mind, is kind of like when you put sugar in your coffee with cream, right? Like it's all becomes part of the liquid. It's part of the chemistry of the seawater. And if we do it right, that's exactly what should happen. If we, unintentionally, if you raise the pH too quickly in a given area, there is studies that people have done and that we're very well aware of that shows that you could end up with a precipitation event. And so we don't want to get anywhere close to that level, right? And that's at when you're exceeding a pH of 9, so you're way over your permitted limit anyways. But that's different. That's where now your calcium carbonate within the seawater, which is already in that liquid form, starts turning into like a solid form and kind of like snowing within the ocean, and which obviously we don't want. And in that process, you're actually going from bicarbonate to carbonate, so you're releasing CO2. So it's exactly what you don't. Not only do you not want it because you're disturbing the environment, but it's counter to what you're trying to do in terms of carbon removal. So some people have been able to force that reaction in a closed system. Our modeling shows that you would have to add way more alkalinity than you could physically in order to trigger that kind of event in an open environment, like where we're working with the power plant right now.
So from the simplified equation, you have the alkaline plus the CO2 goes to HCO3, which is the carbonate, right? But that's dissolved in the water, and it doesn't create an acidic pH level like CO2 dissolved in the water would on its own, right?
That's correct.
But if you have too much alkaline and there's too much reaction, the water can't hold it, and then you get precipitation of this stuff showing up, like you said, snow or whatever in the water, which starts to affect the environment, because now you're getting deposits of the stuff everywhere. And then there may be even more reactions that produces bicarbonate, which causes, imbalances things in a different way, right?
Yeah, so you want to avoid, like, we're trying to do very minimal inputs into the system. Like we wanted to, you want to have a small change over a long period of time over a large area in order to affect high scale carbon removal. So that's the goal.
I see we have a question from Daniel asking if this would work in freshwater systems as well.
So we often get that question, but the answer is no. Like it's the ions within seawater that you're trying to react with the CO2. So I know there are companies, Carbon Run, which operates in an area. They're looking at, they add calcium carbonate, so just limestone to river water that's discharging into an outfall, but the actual removal occurs once that river fresh water has entered into the marine environment. So the short answer is no, but we do get asked that question a lot.
So I thought it was interesting, Jason, that you'd mentioned you're looking for different sources of alkaline at bigger scales, which create opportunities down the road. If there's like capital investment, how do you scale this up, in the long run? That's really interesting. I'm aware of, like, I don't know anything about where you would find these materials, but I maybe just a comment. I'm fascinated by like the global distribution of mines and also ports made specifically for mining all around the coasts of like everywhere, South America, North America. There'll be these port facilities just for getting mining materials onto ships. And I wonder if that might lead to some interesting opportunities about having these byproducts available, and then also kind of near a marine environment, whether you do any kind of mixing there or maybe some integration with shipping where there are systems that, you know, kind of help. The ships are going across the ocean anyway, you know, and then you can take advantage of that. But I mean, obviously that's way in the future, and, you know, that kind of thing, right?
I think you're right. I mean, I think that's where we end up. The reason why we're working with permitted pipes is because there is a framework that we can, you know, trial and develop this technology under that exists today. But in terms of ship-based ocean alkaline enhancement, a lot of people are looking at it. It's been studied, but, you know, we have the London Protocol. You know, there's the, you know, disposal at sea. It gets complicated. International waters, it gets very complicated. And so we're looking to avoid that at this stage. And as we showed sort of at the beginning, the infrastructure exists, the pipes exist, the regulatory framework exists. For today, it makes sense for us to take advantage of that, to demonstrate what we can at this level and learn as much as we can. In terms of the, you know, the mines all over the world, I also find this fascinating. I have a Google Earth tab that's permanently pinned on my browser because I'm constantly looking at these sites. And, you know, even though our first trial involved bringing brucite all the way from China, the issue on the carbon footprint was not about shipping it all the way from China. It was about the amount of times that, like, it ended up in the States. You know, there was some work that was done in the States. It was the number of different times that it had to be moved from one transport to another that really killed us when it came to LCA, life cycle analysis. But like, moving stuff over the ocean isn't as carbon intensive as you thought. So, you know, bringing stuff in from Spain to Halifax actually doesn't create that much of a carbon footprint as, say, moving stuff from like Ontario to Halifax, which is kind of counterintuitive. But you know, when you start moving stuff by train or truck, it's much worse from an emission standpoint than bulk cargo carriers.
Cool. Yeah, how are we doing on questions, guys? We're getting pretty close here, I think, to the end of the talk. We want to let Jason get back to business. Maybe one last question if anyone's got one. Yeah, congrats again, Jason, on the big XPrize win. And it sounds like you guys have a lot of momentum and a really, really good idea. So I'm going to be keeping an eye on you guys for sure. And maybe I'll just let some of the others say thanks as well here.
Well,
Yes,
I mean,
thank you, Jason, for an awesome and inspiring talk. It's nice to see things moving in a new direction, and we'll certainly, as Dustin said, keep an eye on you guys as things evolve. Thank you again.
well, thank you, and thank you again for inviting me. And when I saw marine beers, I was like, "Oh, this sounds great." I'm a little bit disappointed that there was no beer involved, but next time, maybe we can coordinate something with real beer. But I feel there's a couple of questions that came up that I maybe didn't answer adequately, so feel free to follow up with me. My email is just jason@planetarytech.com, and I can send that. Well, Dustin, you have it, so feel free to share it, or anyone can email me, and I can follow up with the right person to get better answers if I didn't answer your question here. But yeah, thank you.
All right, guys, we'll shut it down for now, and everyone have a good rest of your day.
Take care.
Thank you.
All right. Thank you. Thanks, Jason.
Bye.